Hello, and welcome to the presentation. My name is Dhruv Upadhyay. I'm a recently graduated undergrad from University of California, Irvine, and I am here to talk about the paper titled Personalized User Modeling for Sleep Insight. Before we get any further into the presentation, let us talk about why sleep is important. Other than dictating how groggy we feel throughout the next day, sleep deprivation is also linked to many health risks. Studies have shown that chronic sleep deprivation is linked to an increased risk of heart disease, kidney disease, high blood pressure, diabetes, and stroke. Poor sleep quality can also lead to trouble making decisions, solving problems, controlling our emotions and behavior, and coping with change. It has also been linked to depression, suicide, and risk-taking behavior. And if you are still not convinced that a lack of sleep is bad news, studies have shown that being awake for 24 hours will leave you with the sensibilities of an individual with a blood alcohol level of 0.1%. This is past the legal limit in all states. On the other hand, good sleep is linked to improving learning, enhancing problem-solving skills, helping you pay attention, helping to make good decisions, being creative, and on the plus side, it helps you maintain a good mood. So now that we know a little bit about why sleep is important to us, let's talk about ways that we can record it. The current gold standard for recording sleep is a process called polysomnography. Polysomnography records the user's sleep in a controlled sleep lab environment and tracks various metrics such as EEG, airflow, and ECG. All of this data is collected and then it has to be analyzed by a sleep expert in order for the user to get feedback about their sleeping habits. The accuracy of this study, however, comes at a big cost. For one, it's impractical to spend every night in a sleep lab to understand your sleep. And all of the sensors attached to the person during the study, while they do get accurate metrics, also disturbs the person's natural sleep state and doesn't allow us to record that. So now on the other side, we have consumer grade applications. These include applications such as Sleep Cycle, the Oura Ring, and various smartwatches. Consumer grade applications harness the second primary technique that is used to track sleep. This technique is known as actigraphy. Applications such as Sleep Cycle allow a bedside smartphone to track the user's sleep via its mic. More complicated devices, such as the Oura Ring and the smartwatch, use motion sensors and heartbeat monitors to track sleep. While actigraphy provides a less accurate analysis of sleep, as it has less sensors to work with, it is far more accessible to the average user, and it is not cumbersome to use every night, so it is more accurate with regards to showing a person's natural sleeping state. These consumer-grade applications give us the first step into helping us create a personalized sleep model. So sleep literature has shown us that activities performed throughout the day, such as our diet, the work we do, and the exercise we perform, has significant impacts on the quality of sleep that we get. While sleep studies are able to show general population trends, they often fail to offer personalized sleep advice. Currently, there's no way for an individual to take control over their sleep quality and track those results. Sleep is a very personal activity, and we believe the next important frontier to explore in sleep research is the creation and use of a personalized sleep model. As you can see from this diagram, we have identified various important factors that affect a person's sleep, with the center being the most personal and the outer rings representing the environment around the person. Now, how can we go about making the personalized sleep model a reality? We live in an unprecedented era of data generation. Every person generates tons of data relating to their health via their smartphone and their smart devices that they wear. Different devices and applications generate isolated pieces of data about daily activities, such as exercise, sleep, and meal timings. Now, while most of the time this data is kept separate from each other, If we are able to pull all this data together, we're able to create a picture of the person's day with regards to their daily activities and the sleep that happens. With these, we can create a health state of a person and use that state to draw connections between the daily activities that they perform and then the sleep quality that comes about as a result of those daily activities. Once we have aggregated these life logs, we can use cybernetic principles for describing the person's health state. In this work, we have attempted to use these principles to model a personal sleep explanation. This type of principles, however, can be used for other types of chronic diseases, such as managing diabetes or other chronic conditions. At the heart of this cybernetic loop is the personal model, which encodes how different events in a user's life are related to each other and how they impact the user's health state. We have used a form of interval algebra and event mining to create a rule-based, explainable model of the user's sleep that can be used to understand and predict sleep outcomes. We have used an event pattern language derived from Allen's interval algebra to represent temporal relationships between events. Every event pattern has at least two events that are related to each other through a temporal constraint. Let's look at some examples. One might expect that pollution exposure is usually followed by difficulty breathing, and that represents our first example here. We may also see that high humidity events are frequently concurrent with sleep interruptions, and that after alcohol intake, within 3 to 4 hours, sleep interruptions are experienced. We can also use event operations to create new event streams from existing ones. So for example, one that we used in this study was to create an exercise event. And this included events such as running, walking, cycling, and swimming. The idea of a personalized health model is to draw connections between the daily activities a person participates in and their corresponding quality of sleep. Every daily activity performed in a person's life can be recorded and correspondingly divided into lifestyle events. An example of lifestyle events that were used in this study would be known as exercise, meal timings, sleep latency, number of minutes spent awake during sleep, and so on and so forth. These events can be called health interface events, as they are events that are relevant to the user's health state. For example, in this diagram, we can use the user's data to create rules about the relation between the input event of temperature, the output event of sleep quality, while it is under the context of the exercise levels that the person has done in that given day. These rules are created to represent the possible causal relationships that determine the person's behavior and biological outcomes, and they need to be tested while controlling for the effect of confounding factors. For example, we might believe that under the confounding event of high exercise levels, temperature might have a different effect on sleep rather than when the person had exercised a medium amount and or a low amount. This analysis can be accomplished by using hypothesis verification event mining operator, which creates different subsets of input-outcome event pairs based on the values of the confounding factors, and then they find the effect the input event has on that output event. These verified rules can then be used to create a personalized sleep model. So in this example, which is purely theoretical as a context, we might be able to find that under the confounding event of high exercise levels, low temperature is what gets us good sleep. Or that when the person exercises a medium amount, maybe they prefer high temperatures as that's what gets them the best sleep. So now that we have context about event mining and what a sleep model looks like, we can talk about the data that we used in this study. We created our data set by combining data streams generated from a 31-year-old male athlete. The devices we used to gather the data were a smartphone, a Garmin Fenix 5 smartwatch, and an IoT sensor. This IoT sensor was used in order to record both humidity and temperature. To help us adapt our continuous data streams into an event mining framework, we divided the data up by using discrete boundaries. For example, let's take a look at table 1. We divided up the sleep latency event into 3 different sub-events. This included good, average, and poor. So when the person fell asleep within 0 to 15 minutes, we would classify that as a good sleep latency. They got to bed quickly. Now, on the other hand, if they took between 15 to 30 minutes, we would then classify that as an average sleep latency event. Now, and you can see that the other corresponding sleep quality measures have been divided in the table as well. Now, for the daily activities, we used a different table known as table 2 to help us correspondingly divide all of the event streams that were experienced by the person through that day. With this, we can now discretize our data set and leave it open to an event mining form of analysis. So now that we know about our data set and how we transformed it, we can talk about the experiments we performed. For our study, all significance was determined by using Welch's t-tests and a p-value of 0.05. There were 2 types of experiments that we decided to perform. One was focused around finding significant confounding factors that affected the relationship between a certain input event and a certain output sleep quality measure. And the second type of experiment was revolving around finding the average effect of an input event's level that it had on the sleep quality measure. And we will go into more detail within the next few slides. So let's talk about the first type of experiment we would do. And I will be using this heat map here to help me with description of the experiment. So this first type of experiment, as a reminder, was used to determine significant confounding factors that affected the relationship between, in this case, the input event of the minutes awake throughout the day on the output event of awake minutes, which is a sleep quality measure. So this is the baseline levels of minutes awake versus awake minutes. And then we can see when we condition it on the previous night's sleep quality, we ended up creating different distributions. And this shows us that when we had a poor night's sleep last night, we end up changing the distribution for both between greater than 15 and 17 hours awake and less than 15 hours awake, as we have much worse sleep outcomes when the last night's sleep quality was also poor. So this type of experiment could then identify that poor awake minutes is indeed a significant confounding factor that affects the relationship between the input event of minutes awake and the output event sleep quality measure of awake minutes. With these types of experiments, we were able to create a summary image that is now displayed here. So as a little correspondence, we can talk about this, and we can see that the confounding variable of exercise minutes, while many would expect it to be very significant, is actually not as significant as one might think, as it does not affect as many relationships as one would think. Additionally, we can see that another interesting factor to consider is the minutes awake that a person has, as the minutes awake that the person has seems to significantly affect relationships between all of the other input factors and the corresponding output sleep quality factors. By the way, if you can see a square here, that means if you can see a square like this, that means a significance was found. Now let's talk about the second type of experiment we performed. This second type of experiment was dedicated to finding the average effect varying levels of the input event had on the corresponding output event sleep quality measure. So we will use the same heat map to explore this type of relationship. For this one, we would condition on all the types of confounding factors that we could, and then we would choose a baseline category. So in our case, the baseline category that we would compare to would be the category of greater than 17 hours. So then what we would do is, after conditioning on, say, in our example, good awake minutes, we would compare the distribution of the sleep quality measure when the input event was greater than 17 hours to between 15 and 17 hours of awake time and less than 15 hours of awake time. As you can see, if the confounding factor is good awake minutes, distributions don't change much. But another story is seen when the confounding factor is poor awake minutes. As we can see that now the staying up between 15 and 17 hours does indeed affect this relationship. So this would be a significant factor. And then what we would do is keep track of all of the significant differences we found and then average out those differences in order to create this diagram. This diagram tells us that when compared to being awake greater than 17 hours, if we were awake between 15 and 17 hours, on average, we would increase the number of awakenings we had for that nights of sleep by about 0.8. And so on and so forth. We can see pretty interesting metrics and see a pretty comprehensive distribution and description of the person's personal sleep model. An interesting thing to note is that while one variation in the input might positively affect all of the output sleep quality measures, it doesn't necessarily affect all of them. For example, with temperature, a warm temperature when compared to cold temperatures seems to improve awakenings, the awake minutes, and efficiency, but it seems to harm sleep latency. And this is pretty important when we're moving forward in this type of sleep model research to keep a track of. So in conclusion, we have learned that sleep is very important and that personalized sleep models are powerful tools that will be important to the future of sleep healthcare and research. As for future directions, we hope to integrate this causal rule-based model into a recommender system that continuously adapts to the user's new context and new sleeping habits and makes recommendations to them based on the exercise levels they've had throughout the day, or maybe their meal timings, so they can eventually maximize the sleep quality that they get. Other types of inclusions that we would eventually want to have in a complete user sleep model would be a way to track emotions of the person throughout the day, as studies have already shown that stress is indeed an important factor when looking at the next night's quality of sleep. And as I said, we'd want to build a recommender system that adapts to the user and just incorporate more input events and see if we can find any input events that sleep literature maybe has not already identified as important to the next night's quality of sleep. I would like to thank you for listening to this presentation today. And if you have any questions, feel free to contact me at this email, and my colleagues and I will get to you as soon as we can.